Hey folks, Bill Armstrong here. Do another video here. Call this the Week 6 preview. Probably won't be as long as the Week 5 preview. The first section that you look at this week, section 3.4, the book calls it Transformations. And there's not, there's not a whole lot I'm going to say about the transformations. I mean, they are what they are. So as you go through the text and you look at the videos, I'm just going to rattle off things that you should be looking at and be aware of. One is called a horizontal shift. That's when a function is just shifted horizontally. A vertical shift. There's something called a vertical stretch and a vertical compression. There's a horizontal stretch and a horizontal compression. And then finally a reflection about the x-axis. Now I will say, if you're going on to trigonometry, the vertical stretch and vertical compression, so whether you're stretching a graph out or compressing it, you'll see that again in trigonometry, but it's going to have a different name. It's going to be called amplitude. The horizontal, taking a graph and stretching it horizontally or compressing it horizontally, you'd see that in trigonometry as well, but that's going to be called period. So I'm not going to say a whole lot about them because you would see them later on in trigonometry and they would have a different meaning. And in the grand scheme of things, these transformations are, I guess they're just not that important. They're not that big of a deal. I shouldn't say they're not that important. They're not that big of a deal. So let's just do one quick example of the importance that I think should come out of these transformations. So a typical example would be to use the graph of a function, and here I'm saying f of x equals x squared. And it's using graphs of those basic functions. In last week's video I pointed out there were some basic graphs I would expect you to know without using your graphing calculator. F of x equals x squared, that is one of those graphs. So use the graph of f of x equals x squared to graph the function g of x equals, x minus 1 squared plus 3. Okay, something like this x minus 1 quantity squared plus 3, you are going to see that what's embedded in here are some transformations. The first one, x minus 1, that is a horizontal shift. It's taking the graph of x squared and just shifting it to the right 1 unit. Then finally the plus 3 is taking it and shifting it up 3 units. So if I, let's see, if I come over here and I sketch the graph of x squared, so I'll say that's the graph of x squared, and that's a pretty good graph for me. If I do it in stages, and that's kind of what the transformation should be all about, is doing it in stages. First, the first stage would be to get the graph of x minus 1 quantity squared. It's the first part here. It's the horizontal shifting. So that's taking this graph and shifting it to the right 1 unit. So it'd come to the right 1 unit. And that would give me a graph that would look something like this. I don't know if that'll show up or not. I hope it does. I just did dashed lines. The dashed lines here, that's the graph of x minus 1 quantity squared. Then finally, I will do the vertical shift. And that's a vertical shift up 3 units. And for this one, let me graph this in this reddish colored. So I'm taking this graph, this is the x minus 1 quantity squared, and now I'm shifting it up 3 units. So if it comes up 3 units, see 1, 2, 3, means I would have this point here. So my graph of x minus 1 quantity squared plus 3 would look something like this. And I'm running out of space. But that's the graph of x minus 1 quantity squared plus 3. So again, to recap, very briefly here, the transformations I would go through to get this graph, x minus 1 quantity squared plus 3, from x squared, I would take the graph of x squared and I'd shift it to the right 1 unit. That gives me this graph. Then I would shift up 3 units and I'm done. So that's kind of it. That's all I'm going to go over with the transformations of graphs. You can read, you'll see more as you read the section. Okay, after transformations, you're going to learn about the algebra of functions and also something called composite functions. So first, the algebra of functions. You're going to see a definition that basically says if you do the f plus g of x, that the f plus g of x is just simply taking f of x plus g of x. So that's like the addition, the algebra of functions. That's how you would add two functions. F minus g of x. Well, that would just simply be f of x minus g of x. Pretty straightforward. The next one is multiplication. Then if you see the f times g of x, well, that's just simply f of x times g of x. And then finally, the division. When we've added, subtracted, multiplied, we might as well look at the division. F divided by g of x, well, that's just f of x divided by g of x. And this one here has one little special note. The special note that I'll give with 2 asterisks. You can only do this provided g of x is not 0. We don't divide by 0. Heard that last week. So g of x cannot be 0. So let's see. I think I have enough room here. Let's do an example. Let's say I give you the following functions, or you see the following functions. F of x equals x squared plus 3, and g of x equals square root x plus 1. So let's see, let's try doing the following. Let's try doing the f plus g of 3. Well, according to our algebra of functions, this definition that you should see, the f plus g of 3, that's nothing more than doing the f of 3 plus the g of 3. I'm just using this here. And then, remember, last week we saw how to evaluate functions. To get the f of 3, you take 3 and you toss it into function f wherever you see an x. So the 3 comes in here for the x. 3 squared is 9. 9 plus 3 is 12. To get the g of 3, you put 3 into function g wherever you see an x. So 3 comes in here for x. 3 plus 1 is 4. The square root of 4 is 2. So f plus g of 3 is 12 plus 2, which is 14. So now we could quickly, let's do another one. I have enough space here. We could quickly do the f times g of 3, or f divided by g of 3, or f minus g of 3, because it looks like we know the pieces and parts. We have the f of 3 is 12 and the g of 3 is 2. So let's do, the multiplication one. The f times g of 3. That's just simply the f of 3 times the g of 3. And, f of 3, 3 goes in for x. We know f of 3 is 12. g of 3, 3 comes in here for x, and we know g of 3 as 2. So we get f times g of 3 to be 24. So that's the basics of the algebra of functions. All right, folks, next up is composite functions. And to introduce kind of the idea, the concept of composite functions, I'm going to go back to the old blob diagrams. So let me just review the blob diagrams. I used these to introduce the concept of function last week. So keep in mind that what a function does, a function picks up an element in the domain and it sends it over here to an element in the range. So let's just say it picks up some generic x, and let me call this function g. So it picks up a generic x, cranks it through function g, and it drops you off over here at some y value, but I'll just call it g of x. This is what a composite function, what it means, what the concept is. Let's just say after this function takes place, there is another function that picks up this y value and sends it over here. We'll call this function f. So the function f picks up this y value. Function f picks up this g of x, and it sends it over here to what is labeled as f of g of x. So literally that's what a composite function is. It's you do one function and then you do another function. And what we'll be able to determine is, can you come up with a function that skips this middle step? In other words, can you come up with a function that takes you from here over to here, just one function? Now let me call that function h. And the answer to that question is yes. And that's kind of the idea, the concept behind composite functions. So let me now write down what the definition of how you do the composite functions. And keep in mind, a composite function is one function followed by another function. So, you know what, I have enough room over here. I'd like to keep the blob diagram up here when I write down this definition. I'm not going to write down the full-blown definition that you see in the text, just the mechanics of how it works. First off is the notation. This notation signals composition. It looks like it says fog of x, and I may call it fog of x, but what it really means is f composed with g of x. And what that means is you want to, so this is the definition, to do the fog of x, or the f composed of g of x, you rewrite this as f of g of x, which is literally what my blob diagram is showing. This is f of g of x. The other type of composition you could do instead of fog is you could do, well, goff. G composed with f of x. And you rewrite that by saying g of f of x. So those are the two definitions on how you do composition of functions. Let's just use these definitions in an example right now. Let's work through an example. So let me grab my eraser, make some space here. So in this example, let's say we are given f of x is x squared plus 1, and g of x is x minus 3. Let's do two things here. Part A. Let's find f composed of g of x. Let's find the fog of x. Okay, here's what I tell people to do. You see f of g of x, the first thing you do, just write down f of g of x. I mean, it's just writing down the definition, writing down what it means. Now just write down, you're supposed to do f of g of x. Well, what's g of x? G of x is x minus 3. So we're putting x minus 3 in place of g of x. So we have f of x minus 3. G of x is x minus 3. This is just evaluating functions. As I showed last week, we don't freak out. We know it's just a substitution that we do. It doesn't matter if we're doing the f of 2, the f of 3, the f of w, the f of Stewie. It doesn't matter. We evaluate the function. We always evaluate functions the same way. It's a substitution. So you have the f of x minus 3. You are taking this x minus 3 and you are substituting it into function f wherever you see an x. So this x minus 3 comes in here for x. And it gives you x minus 3 quantity squared plus 1. And if you want, you could FOIL this out to get an x squared minus 6x plus 9, and then add the 1 to it, so you could have it simplified down to an x squared minus 6x plus 10. I'm just going to stop right there. Let's try a GOF, a G composed f of x. So part B, let's determine G of f of x, G composed with f of x, the GOF of x. I tell people the first thing to do when you see the G composed with f of x is just to rewrite it as G of f of x. It's using the definition that you will see. And now, what is f of x? F of x is x squared plus 1. So x squared plus 1 is f of x. So go ahead and put x squared plus 1 in place of f of x. And again, we're evaluating a function. We're finding the g of x squared plus 1. So we take the x squared plus 1 and we toss it into function g wherever we see an x. And we get the g of x squared plus 1. We put x squared plus 1 in here for x is x squared plus 1 minus 3, which I'll go ahead and simplify that down to x squared minus 2. I do want you to notice, this is an important observation, FOG and GOF, in general, they do not produce the same thing. Notice here's our FOG, x minus 3 quantity squared plus 1. And here's our GOF, x squared minus 2. These are not equal. In general, FOG does not equal GOF. The only times FOG will equal GOF, the only time this composition will equal this composition, are for very special functions that we will talk about in a little bit. But that's it for compositions. All right, next up, and the last topic that you would be seeing this week, one-to-one functions and inverse functions. Let's start off with one-to-one functions. One-to-one functions are, and you can see the definition in your book, it basically says that for every x in the domain, it goes to only one y value in the range. So every x goes to 1 and only one y value in the range. Graphically or visually, what that means is something called the horizontal line test. Remember last week we looked at the vertical line test. The vertical line test was used to tell us if we had a function, if y, the graph represented y as a function of x. The horizontal line test is going to tell us if our function is a one-to-one function. Just like with the vertical line test, my horizontal line test, the way I word it and the way I look at it, is for a horizontal line test, if I can draw one horizontal line that intersects the graph in more than one point, it is not a one-to-one function. All it takes is one horizontal line to intersect it in more than one point to say not a one-to-one function. Let's do some quick graphs here and quick examples just to make sure we understand the horizontal line test, and that the horizontal line test tells us if our function is a one-to-one function. So let's see. Here's one graph of a function here, part A. And here's another one. And here's a third one. Here we go. Graph of 3 different functions. I don't know what the functions are. I don't care. My question here, are these one-to-one functions? So let's look at the graph in A. It looks like no matter what kind of horizontal line, no matter where I draw a horizontal line, any horizontal line is only going to intersect the graph at one point. No matter where I draw a horizontal line, it intersects the graph in one point only. So that means this most definitely represents a one-to-one function. It's a special function. A one-to-one function is a special function. Now let's look at the graph in B. If I start drawing or imagining horizontal lines, any horizontal line I draw is only going to intersect the graph in B in one point. So here again, the graph in B, does it represent a one-to-one function? Yep, most definitely, thanks to the horizontal line test. Now let's look at the graph in C. It looks like if I draw horizontal lines here, it's only intersecting the graph in one point, or horizontal lines up here, looks like it would only intersect the graph in one point. But if I draw a horizontal line right here, and all it takes is one horizontal line, this horizontal line intersects the graph in 3 points. That means this function is not a one-to-one function. One-to-one functions are special functions. One, they must pass the horizontal line test, but they are special functions, as we will see here in a little bit. Hey, next folks, all this is building up, that we've been talking about here is building up to the idea of an inverse function. Here let me show you, we can't talk about functions, it seems like, without taking a look at the blob diagram. Remember, this is what a function does. A function picks up some number, x, cranks it through the function f, and it drops you off over here at some y value that we call f of x. Remember, this blob represented the domain of function f, and this is the range of function f. Here's what an inverse function will do. An inverse function, let me use this, I don't even know what color chalk this is. An inverse function starts where you were dropped off and it sends you right back to where you started. This is the notation for inverse function. Don't read that as f to the negative 1. You read that as f inverse. Notice in the blobs, since the inverse function is starting here, this blob would be the domain of the inverse function. And over here, this blob is the range of the inverse function. So some important pieces here about inverse functions. First, it looks like a function then followed by its inverse function. They undo each other. Because if you end up right back where you started, you've undid it. I mean, if I went to the bank today and I deposited $300 in my checking account, And then later on today, my wife withdrew $300. I mean, the net effect on my bank account would be zero. It'd be nothing. I'm right back to where I started. It's kind of the concept of an inverse function. Second thing, and this is really important, the domain of the function, that's the domain of f, that's what I have written in white here. The domain of the function must equal exactly the range of the inverse function. And the range of the function, f, the range of the function must equal exactly the domain of the inverse function. So this schematic will be important here in a little bit when we actually start finding inverse functions. But first, a very typical question. If I give you two functions, the question is, are these functions inverses of each other? And here's how you answer the question. Two functions, let me just call them f and g, are inverses if and only if when you do the composition f of g of x, when you do the FOG, you get x. And, let me underline and 3 times because it's important. When you do the GOF, the g composed of f of x, you also get x. So here we are, back to composition of functions. Composition of functions, very important. Just reviewed it a little bit ago. You should have learned it. This is an important application of composition of functions. So, well, here in a minute we'll take a look at an example of whether or not two functions are inverses of each other. All right, back here looking at an example. Giving you two functions, and I'm saying let's show that this function f of x, which is 2x plus 1, and the function g of x, which is x minus 1 over 2, let's show that those two functions are actually inverses of each other. And the only way you have of doing this right now, and the way that I'm going to stress, is you need to determine the f of g of x. See if you get x. So here we go, f of g of x. Well, we know to rewrite the f of g of x as f of g of x. And g of x, here it is, it's x minus 1 over 2. So we put x minus 1 over 2 in here for g of x. Now to determine the f of x minus 1 over 2, we take x minus 1 over 2, toss it in here to function f, toss it in there wherever we see an x, there's only one x. So we have 2 times x minus 1 over 2, and I can't forget the plus 1. Let's simplify this down. I mean, these 2's will cancel out. You're left with x minus 1 plus 1. That simplifies down to x. So check it out, folks. The f of g of x, the FOG of x, is x. Is that enough to show that they are inverses of each other? No. Remember, you have to do two things. You have to do the f of g of x and, remember I underlined and 3 times, the g of f of x. You have to do the GOF. And if we do the g of f of x, where's f of x? Here it is, 2x plus 1. To do the g of 2x plus 1, remember you're just evaluating a function, so you're going to take 2x plus 1, you're going to toss it right in here for x, so you get 2x plus 1 minus 1 over 2. 2x plus 1 came in here for x. 1 minus 1, well, that's 0, so you're left with 2x over 2. That simplifies down to x. We have shown that the FOG of x is x, the GOF of x is x. Because both FOG is x and GOF is x, that's how we know these two functions are inverses of each other. All right, let's tie this all together now. Here a little bit ago we were just talking about one-to-one functions. Now we're talking about inverse functions. We looked at composition of functions, so bringing it all together. And I said that, one-to-one functions, and we determined if a function was a one-to-one function by looking at its graph and checking to see if it passed the horizontal line test. I said those were very special functions. One-to-one functions are the only functions that will have inverse functions. Not every function has an inverse function. Only special functions have inverse functions. Only one-to-one functions have inverse functions. It's very important to remember. Only one-to-one functions have inverse functions. So with that said, there's a process you can go through. If you have a one-to-one function, there is a 4 to 5 step process you can go through to determine the inverse function for whatever one-to-one function you are given. And I'm gonna write down the steps and do them at the same time. Kind of putting it all together here. Let's look at this function. (3x plus 2). Okay, 3x plus 2, it is a one-to-one function. The graph is a line. It's a linear function. So I know it passes the horizontal line test. It is a one-to-one function. Since it's a one-to-one function, it has an inverse function. Here's what we can do to find the inverse function. Step 1. Step 1. Replace f of x with y. So for this function, here's what step 1 would look like. That's it. Pretty easy. Replace f of x with y. Step 2. Switch the variables. So all the x's and y's you see, you switch them. So for this function we're dealing with here, this y would become an x, and that x becomes a y. That's pretty easy. Step 3. Solve for y. So over here, step 3. Here's my equation. I now solve it for y. Well, that's not too bad. I solve for y by subtracting 2 from both sides. And then divide both sides by 3. All right, we're done. We've solved for y. We have y by itself. Step 4. This is another easy step. Replace the variable y with your inverse function notation. So step 4. Here's my variable y. I'm going to replace it with inverse function notation. That's f. That's my inverse function notation. And step 5, different people say different things for step 5. Step 5, some people say for step 5, check your work. And you would check your work by doing the composition of these two functions to make sure you get x back. That's how you know if they're inverse functions. Other people, and I'm kind of one of these type, that would say, and I'm just saying this as it's like a prelude to trigonometry, setting you up if you're going to go on to trigonometry. Make sure you have that domain to range agreement that I showed in the initial blob diagram and talking about inverse functions. In other words, make sure that the domain of this function is equal to the range of the inverse function. Make sure that the range of the function is equal exactly to the domain of the inverse function. But since they're both linear functions. They both have a domain of all real numbers and a range of all real numbers, so that's really nothing to worry about. Actually, what I'm talking about there, you worry about even more in trigonometry. You don't have to worry about it so much now. But this is the basic process that you go through. So if you're asked to determine an inverse function for a given function, the first thing you have to make sure of is that your function is a one-to-one function. Only one-to-one functions have inverse functions. So if you know it's a one-to-one function, that's the process you go through to determine the inverse function. And as you see, we came up with the inverse function over there pretty quickly, pretty effortlessly. The algebra was not too bad. And that's pretty much it for this week 6 preview video. Just like I said for the week 5 preview video, this does not replace actually reading the e-text, looking at the videos, doing the homework, all of that stuff. It's just meant to be a supplement to give you a quick overview, preview, come back and look at it later on if you want, or do whatever you want with it. Again, if you find these videos to be beneficial, let me know. If you don't, let me know that as well. But that's it for the week 6 preview. Thanks for watching.